So at this point, we are ready to define modular arithmetic. And this type of arithmetic, I'm sure most of you, maybe all of you are familiar with this. And let's lay out the rigorous properties here. Modular arithmetic is defined on the set of integers from 0 up to m minus 1, where m is going to be the positive modular value. So for instance, modular arithmetic on, let's say Z3 is defined on the set 0, 1, 2, let's say. Or arithmetic modulo 5 is defined on the set 0, 1, 2, 3, 4. Of course, the elementary operations here are addition and multiplication. Arithmetic modulo m, as we have seen, addition corresponds to modular addition. So a plus b in this arithmetic is equal to a plus b modulo m. Now, this addition is modular addition, and this addition is the normal addition we all know, okay? Simply, for instance, 3 plus 4 modulo 5 is going to be equal to 2, because that is simply 7 modulo 5. Simple as that. Same goes with multiplication. Multiplication here is modular multiplication, but multiplication here is the ordinary multiplication we know. And in modular arithmetic, multiplication corresponds to a times b modulo m. Simple as that. Okay, now here are the properties. And these properties we have seen earlier in the context of the group theory, if you remember. So let's remember what modular arithmetic, what properties modular arithmetic satisfies. First of all, we have closure. Both operations, addition and multiplication, are closed in this set z sub m, the integers from 0 up to m minus 1. And we also have associativity, again, for both operations, a plus b plus c equals a plus b plus c. Same with multiplication. We have identities for both operations. The identity for addition is 0, and the identity for multiplication is 1. And we also have additive inverse. 0 is its additive inverse. And for all other numbers that are not 0, a, let's say the number is a, and its multiplicative inverse, additive inverse is going to be m minus a, right? So for instance, under modulo 5, the additive inverse of 1 is 4, so that when you add them up, you get the additive identity, which is 0. Similarly, the additive inverse of 2 is 3. When you add them up, modulo 5, you get 0, which is the additive identity. Okay, and we have commutativity again for both addition and multiplication, and we have distributivity, and this might be confusing because ordinarily we have distributivity of multiplication over addition in general, but not the other way. However, in modular arithmetic, we have both distributivity of addition over multiplication and multiplication over addition. Now, when you look at these properties, we see that the structure Zm with addition is a commutative group or an abelian group, if you remember. And this structure, the set Z sub m, this set, along with these two operations, addition and multiplication, is a commutative ring. On the other hand, the set Z sub m, along with multiplication, is not a group because multiplicative inverses may not exist in all cases, okay? Depending on the value of m, multiplicative inverses might exist or not. Or it might exist for some elements and might not exist for some others. Therefore, in the general sense, this structure is not a group. Okay, so we talked about addition and multiplication. We don't usually talk about subtraction and division, because subtraction is defined via additive inverse, and division via multiplicative inverse if they exist. And we can also talk about exponentiation because it's just repeated multiplication. But here, of course, we don't really need to compute the exact values in the general set of integers, and we are going to use this result here: a times b modulo m is equal to a modulo m times b modulo m modulo m. So here I'm going to give you an efficient way to compute modulo exponentiation. um, the point here is, for instance, if you encounter a problem like this, what is 3 to the power 644 modulo 645? You should not and do not need to compute this number, 3 to the power 644. Obviously, this is a huge number, and you do not want to work with huge numbers in a numerical way, and therefore, uh, we are not going to actually compute it, and we do not need to compute it. Um, to compute the result of this, and this is under modulo 645, so the result is going to be in the set z sub 645, which is the set of integers from 0 up to 644. Okay, and the idea here is to write the number 3 to power 644 as something like this. Okay, 3 to power 512, 3 to power 128 times 3 to power 4. So you break down the exponent into powers of 2, which you can compute iteratively. See, you start with 3 to power 1, which is obviously 3, and then you take its square. 3 to power 2 is 9 modulo 645. 3 to power 4 is the square of 3 to power 2, which is the square of 9. So it's 81 modulo 645. And next step, you get 3 to power 8, which should be congruent to the square of 81. Now, the square of 81, you compute it and take modulo 645, which is 111. Okay, I don't need the exact value of 3 to power 8, so I don't need to compute, well, I don't need to keep, let's say, the value of the square of 81, but I just keep its modulo 645 congruent value. The next step, 3 to power 16, this is equal to the square of 3 to power 8. But you see, I don't need the exact value of 3 to power 8, nor the exact value of 3 to power 16 based on this rule here. Therefore, instead of the exact value of 3 to power 16, I compute the square of 111 and take modulo 645. And that gives me 66. And you continue like this, 3 to power 32, you take the square of 66 and then take modulo 645, which gives you 486. And then you take the square of this value, take modulo 645, you obtain 126, which is 3 to power 64 modulo 645. Okay, so you continue like this. You get 396 here, and 3 to power 256 modulo 645, you get 81. Now you see there is a cycle here. Since I have reached 81, the next value I don't even need to compute again because I know that it's going to be 111. Okay, so this is a typical behavior. You see these cycles all the time in modular arithmetic, and it eases computations. Now, when you have these values, you can now compute 3 to power 644 modulo 645, because this is simply equal to the product of these three, and therefore the result is going to be this 111 times this 396 times this 81 modulo 645. So Uh, Instead of computing this huge number, 3 to the power 644, you just compute this list and then compute this product and take modulo 645, which gives you 36.